Hello, and thank you for joining us today, wherever you may be. Welcome to the launch of the IEA's Energy Technologies Perspectives Report, the latest instalment of the IEA's flagship technology publication, which examines supply chains for mass manufactured clean energy technologies. My name's Oliver Joy. I'm the communications manager at the IEA. I'm delighted today to be joined by the IEA's Chief Technology Energy Officer, Dr. Timur Gul, and Head of Technology Innovation Unit, Araceli Fernandez, and our Head of Technology Supply Chain, Peter Levi. The report is freely available on the IEA website. We launched it last week, and we'd encourage you to download it and explore its full analysis. Just a quick word on how we will run things today. We will begin with some opening remarks from Dr. Gul. Following that, Araceli and Peter will present the key findings of the report. And after the presentation, we will move to a Q&A with you for everyone tuning in. For viewers participating today, you can submit your questions about the report at any time during using the Zoom Q&A function. And we'll take a short pause after the presentation to allow any final questions to come in. And we do ask if those questions can be about the report. Thank you. And with that, it's my pleasure to hand over to Timur.
Yeah, thank you, Oliver. First of all, good morning, good afternoon, good evening, depending from where you're dialing in. Welcome also from my end to this launch of the 2026 edition of Energy Technology Perspectives. As Oliver said, I'm Chief Energy Technology Officer here and lead the team at the IEA responsible for this work. Really privileged to be here with Araceli and Peter, who will be talking you through the findings of this report. As Oliver already said, ETP is the IEA's flagship technology publication. It is designed to be a guidebook for energy technologies, so it is somewhat pedagogical in its approach, and of course this year is no exception. I should mention that this year is actually the 20th anniversary. So the first edition of Energy Technology Perspectives was actually released in 2006, and I'm pretty sure that many of the veterans, many of the founding fathers of this particular report are listening in to this particular webinar today. And I also know from several among you tuning in that this year's edition, has been eagerly anticipated. Now, of course, these are turbulent times in energy markets, and I should acknowledge that much of the analysis that we'll speak about today has been undertaken before the current events. So the current events are obviously therefore not subject to the debate of the launch presentation. The themes covered in this year's edition of ETP, if anything, though, will be even more important moving forward for many governments around the world. What I would like to do is to highlight three areas from today's report that I believe will matter the most moving forward. The first actually concerns the market for clean energy technologies, so the demand side of the technology equation. The main message here that my colleagues will talk about in a couple of minutes is that there is a shift in the rationale behind the deployment of clean energy technologies, especially those that underpin the age of electricity. Until a couple of years ago, climate targets, reducing air pollution were principal drivers for the deployment of clean energy technologies, but today they are just simply market opportunities for those that produce them. Their combined market value actually surpassed $1 trillion US dollars last year for the first time. Mass manufacturing and falling costs of these technologies are the main reason why the market has grown in recent years. And this mass manufacturing and the falling costs have actually given governments around the world more tools to reach their energy policy goals, including, of course, for energy security. The critical finding of this year's edition of Energy Technology Perspectives is that the outlook for these technologies remains very positive despite policy changes in some countries around the world. In all of IEA's exploratory scenarios that look into the longer-term impacts of current policy settings, we find a growth in the market value of these technologies over the next decade. The second area I wanted to highlight is the area of supply chain concentration for clean energy technologies. The IEA was actually the first to highlight the risks posed by the geographic concentration of supply chains for these technologies. It was featured for the first time in the 2023 edition of Energy Technology Perspectives. In this year's edition, we added two important dimensions to the analysis in this area. The first one lies in the complexity of ensuring resilient technology supply chains, because these are technologies with many, many different components and not a few. What we have done in this year's Energy Technology Perspectives was to apply a so-called N-1 analysis that you may know from the power sector and elsewhere, where you take out the largest supplier across all individual steps of a supply chain in order to identify key vulnerabilities. The analysis we have done covers a wide range of individual components, and what we found is that in each and every single supply chain that we looked at, there is at least one key component for which less than 1/4 of global demand outside China could be met by supply outside China. For solar PV, this is wafers. For batteries, it is cathode precursors and many more. My colleagues will talk about the details in a couple of minutes. Now, of course, disruptions in such supply chains don't have the same immediate energy security impact as is the case for fossil fuels, but they are an important economic security consideration. A factory that produces batteries but does not have access to key components will, in the end, not be able to produce those batteries. The economic impact here is very significant, in particular in the case of battery supply chains, where we find that an interruption of 1 month in Chinese battery supply chain exports could prevent the production of $17 billion worth of electric cars elsewhere, just one individual month. The second novel dimension to our analysis of geographical concentration is in the interdependency of markets. Of course, as I just highlighted, industries around the world are vulnerable to potential supply chain disruptions from China, but so does the success of China's clean technology industry rely on access to these markets. You can already see this in past data. Around 40% of China's solar PV module production growth over the past decade was actually destined for exports, and you can see it in our future projections as well, where we show a similar reliance of China's battery, electric car, and heat pump industry on exports for future production growth. The final theme I wanted to highlight before giving the floor to my colleagues is industrial competitiveness, an important topic for governments around the world, regardless the industry involved, and the manufacturing of clean energy technologies is, of course, no exception here. China is, this will not surprise you, by some distance the cheapest manufacturer in clean technology manufacturing. It can produce clean energy technologies anywhere between 30 to 60% cheaper than other regions around the world. There are multiple reasons here for why Chinese production is so much cheaper, and they differ hugely by technologies. My colleagues will speak to the various reasons in a couple of minutes. But what is important is that addressing these competitiveness gaps is extremely important. Otherwise, if not addressed, industrial competitiveness can become a stumbling block for a range of policy goals, for energy policy, energy security, for economic policy, economic security, and of course, for each country's own climate goals. Decision makers will need to take a clear-eyed view here on what shapes competitiveness for different products and processes. And for clean energy technologies, they will need some creativity for improving it through fostering competitive domestic production on the one hand and through international partnerships on the other hand. I'd like to leave it here. Thank you again for joining us today, and we'll now pass the word on to my colleagues Araceli and Peter to talk you through the finding of this year's report.
Thanks very much, Timo, for the great introduction. Let me just join in this warm welcome to everyone joining us today on this release of the 2026 edition of the Energy Technology Perspectives. And I'll just go directly to diving into some of the key insights that we'll be unpacking today. The first point we wanted to focus on is on the market of clean energy technologies. We see here the greatest growth in terms of demand for these technologies, for those that are related to the age of electricity, as Timo mentioned, those technologies as well that are mass manufactured today. Technologies like solar PV and wind, like electric cars, batteries, heat pumps, and so on. They have all seen important cost reductions over recent years. And at the same time, we also see that as a result, they are increasingly becoming cost effective in different regional contexts and in different configurations. We have estimated that in 2025, the global market size of clean energy technologies reached almost $1.2 trillion US dollars. What we mean by market size here is really the monetary value that is raised by looking at the volumes that are sold multiplied by the price of these individual technologies. And as Timo mentioned, what we see is that strong growth and important growth would be expected when we look over the next decades, no matter in which IEA exploratory scenario. If we look at the CPS, our current policy scenario that basically looks at a future energy system in which there could be no further change into policies that are already adopted, what we see here is that to 2035, the global market for clean energy technologies could double, reaching $2 trillion US dollars, which is equivalent to the market size of the global oil sector that we saw last year. If we look at the STEP scenario, which is our stated policy scenario that takes also into account those policies that are tabled but not yet adopted, what we see is a growth of 2.5 times the levels we saw in 2025. And that's despite the continuous cost reductions that we expect for these technologies as they deployed further as well. Now, there are other clean energy options we've been looking into, and here what we see is that the global markets for those are smaller in terms of their monetary value. If we think about low emission fuels, for example, we've estimated that the global market for those fuels last year was around 215 billion US dollars, and we expect a doubling of that market roughly when we look at the next decade, both in the CPS and in the STEPs. The greatest opportunities here rely to or are hinged on those fuels for which we could make their use in existing infrastructure already, particularly on biofuels, but there are other opportunities as well. We've seen, for example, that the production of low emissions hydrogen has been growing quite significantly, at times higher than often is realized. For example, we saw a growth of 80% on a year-to-year basis last year. If we look at the area of materials, low emissions or zero emission materials, so materials that are basically produced with a lower emissions footprint, we've seen that the market for those materials has been taking or attracting attention in recent years, but at the same time, we haven't seen large operational projects that have really materialized yet. We have seen also a steady growth in the project pipeline of expansions for this type of projects that have been led by different regions across different materials. But at the same time, again, a strong policy support is still needed to unlock these investments further and to make sure that they could scale up. So as a result, what you see in the slide is that we don't see a big increase in absolute terms for the size of these markets in the scenarios that you see in the screen, both in CPS and STEPs moving forward. Now, we've talked about the expansion of clean energy technology markets, but of course, this can only happen thanks to this big enabler, which is the investments in manufacturing capacity, those facilities that really produce and deliver these components and technologies that conform them. What we've seen is that the investment in clean energy technology manufacturing reached around 200 billion US dollars in 2023 when it peaked, and since then it's been declining gradually. One of the key reasons why this manufacturing investment is been declining is because we see at the moment a surplus of manufacturing capacity, particularly in solar PV and batteries. And this basically means that manufacturing capacity in place exceeds the current demand levels that we're seeing in the market. Overall, as you see in the slide, there are thousands of facilities around the world, across 50 countries, producing different components and technologies within this group of key clean energy technologies, from solar PV and wind, electric cars, batteries, electrolyzers, impacts, and so on. But of course, every single facility is different, has a different configuration, has a different utilization rate, different production levels. And also, as I've mentioned before, we at the same time are seeing clean energy technology investments on manufacturing facilities declining, which at the end of the day results on still China remaining the single largest producer of clean energy technologies around the world. When we look at these levels of concentration, this is very clear. What we see is that China is producing already today 80% of the solar PV modules and the batteries that are sold worldwide, 3/4 of the wind nacelles, and 70% of the electric cars that are sold around the world. And if we look at what this concentration could look like at the corporate level, again, this outsized role that China plays in clean energy technology manufacturing is very visible. Just to make this a bit more tangible, we wanted to bring forward a couple of examples here. If we look at solar PV, the largest producer in the world is the Chinese company Jinko Solar, which again could be comfortably supplying all the demand that we see in Europe for solar PV modules at the moment. In the case of wind, for example, another Chinese company again is at the top, Ambition Energy, which has the capacity to produce 35 gigawatts of wind turbines, which is equivalent to around 3 times the overall demand that we see in the whole of Americas. And perhaps just to highlight the most significant example of corporate concentration, which relates to batteries. The largest producer is a Chinese company again, CATL, and it has the capacity to deliver all the demand for batteries that is hosted or that we see outside China, so in the rest of the world already today. Now, one could think that this aspect of regional concentration is a key feature or a unique feature of clean energy technology supply chains, but that's certainly not the case. We also see that, of course, in the case of fossil fuel supplies. We also see that in the case of critical minerals supplies. But one of the key characteristics and unique characteristics of technology supply chains is, as Timur mentioned, they are conformed of different components, which are manufactured goods in themselves. And so this basically means that the resilience implications of technology supply chains are very different compared to those related to fuel supplies. When we look at the resilience of technology supply chains, one supply chain would be only as strong as its weakest link. And it would be very important, of course, then to identify what would be those weakest links, those vulnerabilities. As Timur identified or mentioned before, we have undertaken in this publication a so-called N-1 analysis. In this analysis, basically, we have explored the implications along those supply chains when we were withdrawing from the market the largest supplier, regardless of the cost or regardless of the country that it took place. And so just making an example here to make this more concrete, when we look, for example, at the supply chain for electric cars and batteries, which is a good pointing case, we see that's a supply chain where China's concentration is very visible along the different steps of the supply chain. And at the same time, that specific supply chain has been the source of different announcements for export controls that have been also the source of concern recently. If we focus in the key manufacturing steps, particularly on when it comes to electric cars and batteries, what we see here is that the capacity for producing these technologies outside China can, in principle, deliver the demand that happens as well outside China. And this is particularly because countries have been focusing on ensuring that domestic production could take place in these steps that often, on the downstream side of the supply chains, tend to accumulate the economic activity. What happens when we look at this analysis in the full supply chain, so looking at upstream steps, is what we find a very different picture. Here we see clear vulnerabilities. As Timur mentioned, in this particular supply chain, what we see is that, for example, the demand of cathode precursors outside China could be only satisfied with less than a quarter of that with the production capacity that exists outside China. And this, of course, poses important implications. Not the same type of implications on energy security that we see for fossil fuels, but it has important economic security implications. What we see as well is that when we look at that picture, just looking at also featuring in what are these announced expansions of manufacturing capacity across these different steps. What we see here is that the picture, as you saw, is not changing very much compared to what we're seeing before. So what are the implications of these disruptions, of these vulnerabilities? In this particular case, we have estimated that a disruption of the supplies or the exports from China in terms of batteries could have, of course, a knock-on effect, reducing the possible output that economies will have in terms of electric cars production elsewhere. We have estimated that implication, that impact, would be worth $17 billion per month in terms of losses for factories outside China that are producing electric cars and that are normally getting their batteries they use from China. But what is also important to highlight is that, as we've mentioned, we've carried out this particular analysis across a full range of clean energy technologies, and it was very important to see that such vulnerabilities exist as well across all these different technology supply chains. Actually, it was we could identify at least one of weakest step for which only less than a quarter of the demand taking place outside China could be met with production capacity outside China. In the case of solar PVs, wafers. In the case of wind, it's about refining rare earths as well as getting permanent magnets produced. In the case of heat pumps, is rotary compressors. So again, a common denominator, which is that every clean energy technology supply chain has a weakest link that would be important to address to ensure that, again, economic security implications will be addressed at the same time. And then I'll hand it over to Peter to continue that presentation. Thank you.
Thanks very much, Araceli. So I'm going to talk to the topic of trade in clean energy technologies, which is a topic that's been front and center recently, thanks in part to a highly dynamic policy environment of late. Despite ongoing trade tensions and at the same time falling prices of many of the clean technologies that we focus on in this edition of ETP, the gross value of international trade in clean energy technologies reached a new high in the second quarter of 2025. China's exports, which are a big part of this, of course, continue to rise, and they hit around $165 billion last year. You may have seen reports that came out last year that China's overall goods trade surplus hit $1.2 trillion for the first time. These clean tech exports would be equivalent in value terms to around 15% of that. And when we take a closer look at global trade in a broader context, it really underscores the point that both Timo and Araceli have made, that clean energy technologies are no longer just driven by climate policy, but they are driven by a broad range of drivers, and they are large markets in and of themselves. If we compare global trade in these gross terms, gross value of trade in clean technologies, to other technologies and commodities that are associated with the energy system, if we take things like grid technologies like transformers, battery minerals like lithium and nickel, and even mature markets for bulk commodities like steel and aluminium, we actually find similar orders of magnitude in terms of the gross traded value and similar participation and concentration among the top three countries involved. Another way to look at this is on a net basis, so through net energy trade balances. What we can see today is that the net value of clean energy technologies remains far smaller than the comparator that we're using here, which is the net trade in oil. Even in China, its substantial clean tech exports surplus is still outweighed by its oil imports, which were around 2.5 times larger in 2024 in value terms. But of course, today's trade in clean energy technologies influences tomorrow's trade in oil and other fossil fuels. And when we look ahead under the stated policy scenario, in this projection, global oil trade does remain more than twice the value of trade in clean energy technologies by the end of the decade in the projection, but there are some important shifts underway underpinning that. So firstly, Europe sees a strong increase in its net imports of clean energy technologies, but that in turn helps it to reduce reliance on imports of oil and therefore reduces its import bill for oil. China's exports, clean tech exports, more than double over this same decade period, such that they are broadly equivalent to its net oil import bill in value terms. Sticking with China and returning to the example that Timur raised in his opening remarks, the kind of outsized role of China in global clean energy technology markets is hard to overstate. But conversely, the role of other countries' markets in shaping China's clean tech industry is also very important. If we take solar PV module production as an example, over the past decade, output in China has risen 13-fold and now stands at about 0.5 terawatt per year. A large share of this growth has been to serve China's domestic market, the portion shown in red here, but around 40% of the increase in production over that decade went to exports, which underlines this enabling role that international markets have played in the ascendancy of China's PV industry. If we take that same projection that I mentioned before in the net energy trade balances and project forward in the stated policy scenario 10 years, we see similar patterns, as Timur mentioned, emerging across some of the other technologies within scope in our manufacturing and trade modelling. Between 40% and 50% of the growth in the production in China of these three technologies shown here, battery cells, electric cars, and heat pumps, are destined for exports in this scenario. Of course, this outlook that we paint a picture of here depends heavily on the policies adopted in other importing regions around the world, energy policies, industrial policies, trade policy settings. These will all affect the pace at which clean technologies are deployed on the one hand, and then the extent to which China and other suppliers can gain market access on the other hand. The sharp decline in profitability that we've seen among Chinese manufacturers of solar PV modules in recent years, which has been driven by oversupply in that industry and also intense competition and involution, as it's referred to, is a clear reminder of what happens when global demand, national demand, does not keep pace with the rate of manufacturing capacity expansion. China's rapid growth that we saw there for solar PV historically and the projection for the other technologies in the stated policy scenario is closely tied to its competitiveness. And competitiveness is really a key focus theme in this edition of ETP. Of course, many factors shape competitiveness, including subsidies, tax regimes, labour laws, permitting processes, and so on. But for our analysis, we are examining firm-level investment and production costs based on data from hundreds of facilities that manufacture these clean energy technologies. And our aim has really been to understand what is physically and in a kind of tangible sense underpinning this competitive edge that China displays. At the top level, the results are shown here, and the message is clear. China's production cost advantage ranges from 30% to 65%, as Timur mentioned at the beginning, across these technologies that are in focus in ETP. When we dive into the drivers of this of the cost differences between China and the European Union, which is shown as our benchmark here, the picture becomes a bit more complex. And by the way, if we were to compare the China's cost advantage to other advanced economies, say in the case of North America, we would find similar cost advantages, but perhaps with a more muted impact on energy. But as I said, when we dig into the cost drivers, the drivers of this cost advantage, the picture becomes more nuanced, and different drivers apply to different technologies. They include things like plant construction and equipment costs, labor costs, energy costs, and so on. Let me just take a couple of examples. So for solar PV, energy costs are by far the most significant portion of the explanation for this cost advantage that China has. over 40% of China's cost advantage is attributable to these energy costs. And this reflects the highly energy intensive nature, particularly of the upstream steps in supply chains for solar PV, wafer production, polysilicon production, etc. This is where access to low cost electricity can really make a substantial difference in terms of the cost advantage between regions. For wind, the dominant factor here is really labour costs. This is particularly true in a direct sense for blade manufacturing, but also in an indirect sense for nacelle production, where material-intensive components of nacelles like gearboxes, generators, etc., also require skilled labour as an input, and so labour costs can have a meaningful impact on the final production costs. For batteries, much of the cost difference can be explained by manufacturing efficiencies and the higher levels of automation that we would see in Chinese factories today. Plants in China can achieve yield rates of 90%, meaning that fewer than 10% of the battery cells that come off the production line fail quality assurance tests that they're subjected to. In the European Union, used as our comparator here, this failure rate can be 2 to 3 times higher. So this analysis really underscores the point that Timur made at the beginning, that the competitiveness gaps, if they're not addressed, could really become a hurdle for many policy goals, from economic security through to the pace and scale of energy transitions. But the reality is that these competitiveness gaps, in the examples I showed before with China, cannot be closed by many countries acting on their own. And strategic partnerships is one mechanism via which countries can seek to increase diversification in their supply chains, but also maintain or boost their competitiveness at the same time. The word partnership has become something of a buzzword in supply chain circles and discussions, and our aim in this edition of ETP has been really to unpack what that means and show kind of tangible examples, concrete examples of what the benefits can be. If we take solar PV as the example again, as I mentioned earlier, these particularly the upstream steps in these supply chains are highly energy intensive. We're talking about polysilicon production, wafer production in particular. Importing these components from regions with lower energy prices, like perhaps some countries in North Africa, to higher cost regions, like potentially some countries in the EU, could today reduce the cost gap with China by around 40%, while in this example still keeping the higher value add manufacturing steps in the higher production cost location. Wind turbine manufacturing, another example we explore in the book here. Again, as I mentioned before, labour costs are the key driver of China's cost advantage, and here we identify India as a promising partner. The country has a long established role in the global wind industry. It's home to several turbine and gearbox manufacturers, and our analysis suggests that India's production costs are only about 10% higher than China's, and the majority, the main reason underpinning this cost difference is more to do with material and component costs and less to do with directly with labour costs. Of course, none of these examples that we explore here or in the book are meant to be prescriptive, and there are many factors beyond just the production cost dimension that we are examining here. While very important, there are many other factors that would influence whether partnerships between two partners, two countries would make sense or not. And of course, it's very important to for a country to have at least a semblance of an existing industrial base and manufacturing base in order to have a foothold to build these complex supply chains upon for a partnership to make sense. Nonetheless, we hope the analysis, the illustrative examples that we explore in the analysis help with the considerations that governments are facing around these strategic partnerships and also other aspects of their industrial strategies. So with that, I leave it there and I'll pass back to moderator Oliver.
Thank you, everyone, for that excellent presentation. So this is where you come in. We now take a short break. You can pose a question in the Zoom chat and we can pick them up following the break. With an appreciation that everything that is going on in the world today, we really would be great if we can stick to what is outlined in the report. Please include your name and organisation with your question, and we will see you shortly. Thank you. Welcome back, everyone. Thank you for the many questions that are coming in. We've got quite a few. We'll try and get through as many as we can. So let's crack on. On that headline figure, we've got the 2 trillion figure with the market potentially doubling by 2035. Where do you see the biggest bottlenecks to scaling up this level of investment and manufacturing capacity? Maybe Timo, we can come to you on that. And then a second question, this for you, Araceli. Can you highlight the role of R&D in the competition, China versus the rest of the world? So maybe Timo, we start with 2 trillion.
Yeah, sure. So I think first and foremost is worth highlighting that this 2 trillion figure, and in fact in our stated policy scenario, it grows even further. This is very much technologies that underpin the age of electricity, as we refer to it here. That's on the demand side, electric cars, batteries, of course. That's renewable energies. That's heat pumps. What is important here is that for most of these technologies, at least under stated policies, availability of manufacturing capacity is not really an issue. We have, especially in the case of solar PV batteries, even electric cars, we have ample manufacturing capacity already now to comfortably even exceed the level of deployment that we have in our exploratory policy-driven type of scenarios. But of course, there are many barriers to tap into the market opportunity. There are many policy efforts that are being undertaken in order to overcome them, and that's part of our deployment modeling of these type of things, as you find it in the energy technology perspectives, but of course also the World Energy Outlook. So perhaps worth reminding of some of them. In the case of electric cars and by extension batteries, they are the single largest market opportunity here, just given the sheer value that electric cars actually have, and cars more generally. Electric cars are increasingly available, increasingly affordable, in fact, in many countries, in particular in China, but also through exports in many countries of Southeast Asia. So the policy challenge here is to overcome key bottlenecks such as recharging infrastructure, to make it available, to build consumer confidence, increase convenience for consumers in order to make use of them. And when it comes to renewable energies, the deployment here really lies on the timely expansion and improvement of electricity grids, including through facilitating rapid, effective permitting processes. There is a huge investment that is required, 60% higher roughly, in 10 years of time compared with today, regardless the exploratory scenarios that you look into. So there are many challenges to overcome, and I saw that there was another question related to that in the chat, how this will play out in our 2026 scenarios. Of course, we're looking into this right now. Many things are, of course, currently on the move in energy markets, and we'll need to see how things are playing out. But these kind of constraints, bottlenecks, will certainly be important priorities for governments moving forward for clean energy technology deployment.
Thank you, Timo. Araceli, that question on R&D.
Sure, thanks, Sylvia. It's a very important point because indeed, I mean, the role that China has played in terms of clean energy technology innovation, it's really crucial, not only for the levels of deployment that we're seeing in that particular market, but also in terms of how competitive they have managed to get. We've seen important milestones when it comes to technology development coming from China, again, not only in the performance and the designs of these technologies, but also in the equipment and the manufacturing processes, really to produce these technologies at scale, which really has contributed for China to have this outsized role, as we have seen in the presentation in clean energy technology manufacturing. We in the team at the IEA, we look at different energy technology innovation aspects. We have gathered all the work that we do in tracking different metrics related to that in our State of Energy Innovation report, which is something that we're publishing every year. We just released it, the last one very recently. And there we look at different aspects of that. I mean, looking at patents, venture capital deals, R&D spending, etc. And maybe just to put things a bit in context in terms of the again, the increasing role that China is playing in energy technology innovation. We saw a doubling of the number of energy patents hosted in China between 2020 and 2023, really reaching the levels that we're seeing now in other countries like the US, Japan, Europe, that have been for a longer time more established in that role. And there's been important also milestones when it comes to technology development. Last year, from perovskite technology for solar from solid states, from batteries to solid cooling as well. So a lot of developments, again, not only on the technology development side in terms of designs, but also on the manufacturing, which is perhaps what makes it a bit more distinct from other contexts.
Right. And how important are those? How important is that patent issue when we come to talking about such a fast-moving market?
It is very important, of course, because it is the step that, in a way secures and de-risks a bit, the deployment that one could see of that technology in the market. And it's a very important step to make sure that, some of the partnerships we were discussing before, for example, that Peter was highlighting, it's very important to discuss all those details on how these partnerships can be win-win situations where there could be, again, knowledge gain and benefits on both sides. So it's quite important to establish very well patents, again, not only related to technology design, but also to the manufacturing processes.
On that point about benefits on both sides, we have actually had a question. We couldn't avoid it on tariffs. Peter, maybe we come to you on that one. When we talk about what has been the impact of the latest US Supreme Court decisions around the International Emergency Economic Powers Act, I think, of tariffs, are clean tech's much cheaper now than previously, given that the tariffs are capped at that 15% level?
Thanks very much, Oliver, for the question. So this ruling that took place recently has yes, indeed, had an impact on the overall rate of tariff that is levied on imports from certain countries to the United States. But the impact on global trade in clean energy technologies is relatively modest. The United States, of those gross import figures that I showed on the slide earlier, the United States accounts for around 15% of global gross imports. So the global impact on the picture of trade policy settings is relatively limited. And for the US specifically, this is more of a change in legal basis than a change in policy direction, at least as we're interpreting it. We have actually done some analysis on the impact of that ruling, because it's not included within the base year policy settings that we model, but we wanted to understand for specific individual clean techs and components what the impact were and what the impact of that change was. And because of the presence of these countervailing duties, anti-dumping duties that are set at much higher levels than the kind of national tariff setting that was concerned by the ruling, the impact, as I say, was relatively modest and did have some different impacts between technologies, and this was more to do with the trading partner that we were talking about in each technology's case. So for the case of battery electric vehicles, the kind of combined average rate that we compute, the average across all trading partners going into US markets, it was almost no change. This is the majority of those vehicles that were being imported were coming from Mexico, and they benefit from preferential arrangements under existing trade agreements. If we take wind components as a contrasting example, there the impact was visible because the national rates that were applied on China and India, I think, accounted for had more of an impact because those countries account for more of the inputs for the imports to the US. So yeah, but again, from an overall kind of clean tech perspective, the impacts of this we think will be relatively modest.
Yeah, very interesting. Araceli, maybe we'll come back to you. We've had another one on disruption to supply chains. Can you elaborate on your estimates of cost of disruption to supply chains?
Sure. Thanks, Oliver. Yeah, so this relates a bit to this vulnerability assessment that we have been a bit unpacking in the presentation. Basically, what we did was to look at again understanding the positioning of the different players across the different steps of the supply chain and their interdependencies. So what trade, of course, takes place in between different steps of supply chains. And in this N-1 analysis basically implies that the largest supplier of a particular step in that supply chain would be taken out from the market, basically meaning that that level of production, that supply would not take place in that hypothetical scenario. And then what would be then the implications for, again, downstream in that supply chain effects. So industrial facilities that would be placed in countries outside that largest supply country, in this case China, that would have to decrease the level of production because they would run out of, say, different components or different inputs that would require for their production processes. That analysis has been done in a kind of hypothetical context, meaning that we're trying to understand and give a sense and an order of magnitude of the size of the economic losses for these downstream dependent factories. But of course, what we didn't look into is, over time, if that was to happen, what would be some of the reallocations and rerouting of some of the trade flows that could take place. But of course, it is important to consider here that, again, the gap that the largest producer leaves in the market for downstream economic activities is very large, looking at the numbers that we're showing. And again, that considering that, again, the whole supply chain almost kind of depends on this weakest link, which ultimately we've seen that has a gap of almost 3/4 of the overall supply. So only outside the largest producer, only a quarter of the demand could be supplied. And the number we've just gave, there are more examples in the book, but the number we gave focusing on electric cars and battery supply chains relates to the economic loss of electric car producers outside China if the export of batteries from China were to stop. So that would imply a $17 billion loss per month overall, with regions like European Union mostly affected because, again, of the dependencies on trade flows in particular.
Okay. And Peter, just on Araceli's point there, if we're talking about production costs in China not being equaled, how do other countries, other governments support these industries and ensure that there is that diverse, secure supply chain? Yeah,
absolutely. So, what we say about this in ETP and in our other kind of publications related to this series is that it's not for the IEA to set the risk appetite of a country or to say exactly what the kind of policy mix should be. It's not our role to be prescriptive in that domain. But we can identify, in certain instances, some sort of win-wins and strategies that might be kind of clearly advantageous in a given circumstance. I would kind of, to be more specific, refer to some of the examples that we gave in the presentation, different forms of partnerships. So we highlighted 2 examples there on solar and wind, where you're really looking to see whether in your partner, as in a partnering arrangement, what are the kind of comparative advantages that each of you can play to get to a lower overall production cost across the supply chain. The solar PV example, the energy costs were raised, the wind example, the labor costs were raised. We also, in some work that we did in the future of the global car industry last year, highlighted some of the partnerships that could be, the partnership arrangements that could be obtained through incentives for domestic investment, potentially in higher cost regions, where the kind of cutting edge of the battery industry is incentivized to invest in locations where perhaps still not approaching the frontier. So the partnerships take many forms, and I think they get to this point in the question that you mentioned, that how can you increase diversification and at the same time kind of maintain or boost your cost competitiveness.
Okay. I think we've got time for one more, so appropriate perhaps, Tima, that we come back to you on this. We saw EU dominance in these markets in the past. Why is the ETP so focused on China? And we have heard from Peter, the outsized role, and it seems to be a recurring theme throughout the report. So why, and if that's correct, why is the ETP so focused on one country?
Yeah, thanks Thanks, Oliver. And it's indeed a good question. And I should say there are many good questions here in the chat. I'm very sorry that we don't have enough time to go through all of them. It's more than a dozen open questions here that I'm seeing here. So I can only encourage everyone to have a look at the report. There is actually a full chapter dedicated to 10 key questions on clean energy technologies. I hope it covers at least. I mean, I saw questions on hydrogen, for example, and many others. I hope some of it you will find answered in the report itself. Now, to the question, I think there is no IEA, and indeed no energy report that can look at the energy sector without looking at China. I'm pretty sure if you make a quick search to typical reports in this space, you will find that the country that is most referred to is typically China. This is very easily and very obviously answered by the fact that China is just simply the largest producer and consumer of energy. It's also the largest emitter of CO2. So there are many, many different reasons in every single part of the energy sector why looking at China, what's happening in China, makes particular sense. For this particular report, the Energy Technology Perspectives, the focus is on energy technologies. And obviously, there's no exception here. China is just far and away the largest player in this market, thanks to many policy decisions, many industry decisions that have been taken over the last decade or so. And with this pedagogical approach that we are trying to take in this technology work, in the energy technology perspectives in particular, for us it was important to understand what, and keeps on being important to understand, what has driven China's success, how can you explain it? There are many countries, many other stakeholders who want to learn from that, actually. I see a question in the chat here where one of the participants would like to understand the technology cost difference, not only between China and EU, but also countries like South Africa and Canada. These are legitimate policy questions, industry questions to be answered, and this is what explains why China just features so much in our work. It's just an incredibly important actor in the energy space.
Well, thank you all for the insights and presentations today. It's been great. As Timo mentioned, Energy Technology Perspectives is freely available online on the IEA website. You can also find on our events page all our upcoming analysis and publications that are due out soon. For the journalists on the call, I would say if you do have any questions of any kind, you can contact the IEA press office and we will get back to you as soon as possible. So with that, thank you for joining us today and have a great afternoon.